effect of non-linearities on the operation of transformer. That is, let us suppose if this is the alternator which is providing sinusoidal output, and this output is being fed to the load, and load requires the pure sinusoidal input for its proper functioning, and as power being transmitted and distributed to the load through transmission lines and distribution lines which are of thousands of kilometers of length. So to provide necessary voltage levels to the load, here we are making use of transformer. And the question here is that if you are providing sinusoidal input to the transformer, whether it is giving sinusoidal output or not, because load requires sinusoidal input. So if transformer provides sinusoidal output, then it is okay. But if the output from transformer is not sinusoidal, then load will not perform to what it is expected to do. And after the discussion on this, you will come to know what is the type of input that to be applied to the transformer to get a sinusoidal output, and which is required by the load for its smooth functioning. And to understand this, it is important to recall the concept of harmonics, which is already discussed in alternator lecture 3. And in this discussion, we will also come across the importance of using BH Castex in transformers. Now, let's recall the concept of harmonics. According to Fourier analysis, any non-sinusoidal signal is the combination of sinusoidal signals of different frequencies, which is represented like this: A1 sine omega t, A2 sine 2 omega t, plus A3 sine 3 omega t, plus A4 sine 4 omega t, plus A5 sine 5 omega t, plus so and so. And of these sinusoidal signals, first signal represents the fundamental signal, which is our required signal. And because of all these remaining sinusoidal signals, our fundamental signal is becoming non-sinusoidal signal. So is why all these signals are called harmonics. So here these signals are the combination of even signals and odd signals. And as these even signals are symmetric about x-axis, they will be 0. So the only harmonics which are present here are odd harmonics. And these odd harmonics are having an order of 3m plus or minus 1 and 3m. That is odd harmonic signals of 3, 5, 7, 9, 11, 13 and etc. And of these harmonics, the most dominant harmonic is the third order harmonic, that is this signal. And because of this third order harmonic, our fundamental signal is getting maximum distortion. So our focus must be on how to reduce this third order harmonic. And of these odd harmonics, few are called positive sequence harmonics and few are called negative sequence harmonics. That is, in power systems, the preferred phase sequence is R, Y and B. That is, R at an angle 0 and Y at an angle minus 120 degrees and B at an angle minus 240 degrees. And this minus 240 degrees can also be represented as plus 120 degrees. Now let's check the phase sequence of 5th and 7th harmonic. That is, for M is equal to 1. So the 5th harmonic, the phase sequence is R at an angle 0 degrees, Y at an angle minus 120 into 5 and B at an angle minus 240 into 5. That implies R at an angle 0 degrees and Y at an angle minus 600 degrees and B at an angle minus 240 can be represented as plus 120. So plus 120 into 5 plus 600 degrees. And it is known that 360 degrees equals to 0 degrees, which implies R at an angle 0 degrees and Y at an angle minus 240 degrees and B at an angle plus 240 degrees. And that implies R at an angle 0 degrees and Y at an angle plus 120 degrees and B at an angle minus 120 degrees. So the phase sequence is R and Y at an angle plus 120. So plus 120 means this is plus 120. So this is Y, and B is at an angle minus 120. That is B. So if you compare this phase sequence with the fundamental signal phase sequence, as it is reversed, so this represents negative phase sequence signal. Now let's check the phase sequence for 7th harmonic. So R at an angle 0 degrees into 7, and Y at an angle minus 120 degrees into 7, and B at an angle plus 120 into 7. That implies R at an angle 0 degrees and Y at an angle minus 840 degrees and B at an angle plus 840 degrees. That implies R at an angle 0 degrees as 360 degrees is equal to 0, which implies Y at an angle minus 120 degrees and B at an angle plus 120 degrees. Now let's draw the phase sequence. So R at an angle 0 and Y at an angle minus 120 means this is minus 120. So Y is here and B is at plus 120. So B at an angle plus 120 degrees. So if you compare this phase sequence with the fundamental phase sequence signal, as these both are same, which implies that 7th harmonic comes under positive phase sequence. Therefore, the harmonics of order 3m plus 1 comes under positive phase sequence signals, and the harmonics of order 3m minus 1 comes under negative phase sequence signals. Now let's discuss about the odd harmonics of order 3m. For m is equal to 1, 3m is equal to 3. That implies phase sequence is R at an angle 0 degrees and Y at an angle minus 120 into 3 and B at an angle plus 120 into 3. That implies R at an angle 0 degrees and 120 into 3 is 360 degrees, which is equal to 0. And similarly B at an angle plus 120 into 3 plus 0 degrees. So B at an angle 0 degrees. And if you observe here that there is no phase difference between any phase, therefore the odd harmonics of order 3m are called as zero phase sequence harmonics, or also called as cophasors, because they have magnitude but there is no phase difference between any phase. And as they are of order 3m, so is why they are also called as triplet harmonics. In power system, let us consider three-phase system. All the components of current will have path from phase to phase or line to line if it satisfies the fundamental property, that is, the phase difference between any component is 120 degrees and the component summation is equal to 0. If they satisfy these two conditions, then we can say that the components will have the path from phase to phase or from line to line. Let's understand this. That is, if suppose this is the alternator from where the energy is being generated, let this be the R phase, Y phase and B phase, because the preferred phase sequence is RYB, and that generated energy from the alternator is being transmitted and distributed to the loads. Let us consider this to be the three-phase load, and now let us suppose that ER is the EMF induced in phase R and EY be the EMF induced in phase Y and EB be the EMF induced in phase B. And as it is discussed that a non-sinusoidal signal will have fundamental signal and harmonics, and for simplicity let us consider only third order harmonic because it is the most dominant harmonic. And similarly EY is equal to E small y and E 3y, and similarly EB is equal to E small b plus E 3b. And as it is discussed that ER at an angle 0 and EY at an angle minus 120 and EB at an angle minus 240, which means that the instant load is connected to the alternator at 0. The current due to ER will start flowing, and after 120 degrees phase lag, IY current will start, and for further 120 degrees phase lag, IB current will start. The point you must note here is that for IR current to flow freely, there is no opposition from IY or IB because they will start after 120 degrees lag. Therefore, IR will complete its cycle freely, either this path or this path. So is why it is said that the components which are satisfying this fundamental property, that is the phase difference between each component is 120 degrees, and they satisfy IR plus IY plus IB is equal to 0. And this you can clearly understand after the discussion on third order harmonic. Now let's discuss that. So ER third order harmonic, as it is discussed, that E3R at an angle 0 and E3Y at an angle 0 and E3B at an angle 0, because these comes under triplet harmonics which are cophasors. So is why the phase difference between any component is 0, which means that the instant load is connected at 0 instant. The current due to E3R, that is I3R, and the current due to E3Y, that is I3Y, and the current due to E3B, that is I3B. All these currents due to these harmonic component will start at the same instant, means I3R, I3Y and I3B. All these start at same instant, and they reach the point at same instant. And what you must note here is that for the current I3R to flow, there is opposition from I3Y and there is opposition from I3B. So there is no path for I3R. Similarly, there will be no path for I3Y and there will be no path for I3B. Therefore, these currents can't complete the cycle through any path. Therefore, the currents I3R, I3Y and I3B are 0, which means that the third order harmonics remains in the phases itself. In lines, they are 0. As there is no path for the third order harmonic currents, therefore they remain in the phases. Therefore, to reduce the third order harmonics, it is important to provide the path for the third order harmonic currents, and by making the neutral connection here, the third order harmonics are reduced to 0. And now we can have the pure sinusoidal output from the alternator phases. And now here comes the importance of the BH Castex in transformers. So for ideal transformer, for sinusoidal magnetizing current, flux setup in the core is sinusoidal, which means that for increase in current I, there will be increase in flux phi. That is, from here to here, as current is increasing, flux phi is also increasing from here to here. Means BH Castex will be like this. And now, as current is decreasing from here to here, flux is also decreasing from maximum to 0. Means now BH Castex like this to 0. And from negative side, as current I mu is decreasing, phi is also decreasing, means BH Castex will move like this. And from here to here, as current is increasing, flux is also increasing from here to 0. Means BH Castex will travel like this. So finally, the BH Castex for ideal transformer is linear Castex, and this is what the BH Castex for ideal transformer. Now let's see the case of practical transformer. This is the BH Castex for a practical transformer, that is, with increase in current I, flux phi increases, so the Castex will be linear up to certain point, and when the core starts saturating, this curve will not be linear no more. There will be a bend like this. And when the core attains saturation, though we increase the current I, there will be no further increase in flux phi. So the curve will be constant like this, because there will be no increase in flux phi with increase in current I after saturation. And now if you demagnetize the core, that is, if you decrease the magnetizing current, the path of the Castex will not be the previous path, as which is happened in ideal case. It will be like this. And now when the magnetizing current is 0, the path of the Castex will be at B, and this point B represents the retentivity, and point C represents the coercitivity. Retentivity will represent the ability of matic material to store the residual flux. That is, ideally, for zero magnetizing current, the flux in the core must be zero. But practically, after saturation, though the magnetizing current is zero, there will be some residual flux stored in the matic core material. So, retentivity will represent the ability of matic core material to store the matic flux, which is residual flux. And now with reversal magnetism, the Castex path will be from B to C. And now if you observe that the Castex has reached C, and this point C represents the coercitivity. This will represent the amount of reversal magnetism that to be applied to the matic core to bring the residual flux to zero. And now with further decrease in current I, Castex will follow like this, and in reverse direction magnetic core will attain saturation, so there will be no further decrease in the flux phi, and the Castex will be constant. And now with increase in current I, Castex path will be like this and reaches point E and then point F. Here our focus is not on the discussion of BH Castex. It is to decide the type of input that to be applied to a transformer to get sinusoidal output. Let's consider the sinusoidal input to the transformer. That is, input to the transformer is assumed to be sinusoidal. From the BH Castex, with increase in current I, there is increase in flux phi, and then when the core attains saturation, the Castex are constant. And now with decrease in current I, the Castex will follow this path, and when current I reaches 0, then the curve reaches point B, and this point 0 is called current 0 point. And then with reversal magnetism, curve will trace the path B to C, and this point C represents the flux 0 point, which means that current leads the flux, means flux 0 point will be here and current 0 point will be leading, means flux 0 point will be here, which means that current I leads and flux phi lags. So now with increase in current I, flux phi will increase and it will follow the magnetizing current I mu, and when the core starts attaining the saturation, the linear Castex will now bend. So this implies that for further increase in flux phi, it needs more increase in current I. So this way the Castex are constant here, but when the core attains saturation, there will be no further increase in flux phi. So from here to here, as the core enters into saturation, there is no increase in flux phi. So flux phi will be constant. And when the current I mu is 0, there will be some flux which is called residual flux and which is represented here with OB. So for 0 current, there will be some flux. So let that point be here. And as with decrease in current I, flux phi will follow the same. So like this. And in reverse direction, with further decrease in current I, core enters into saturation, so there will be no further decrease in the flux phi, which means the Castex are constant like this, which means flux phi is constant. And now when the current reaches 0, there is some residual flux which is represented with OE. So when the current I mu is 0, there is some flux phi, means the point is here. So the curve will be like this. So with sinusoidal input current, we got this type of flux setup in the core as E is equal to N d phi by dt. Let's trace out the induced EMF waveform. That implies that when flux increases from A1 to B1, so this is of sinusoidal nature, therefore E is of cosine nature, it will follow the same, that is from here to here, and from B1 to C1 it is a constant signal. And from the subject signals and systems, there is a concept that impulse function delta of t is equal to d by dt of unit function. As here constant function, let us suppose this to be unit function, and induced EMF is derivative of that unit function. So here from B1 to C1, here we will get the impulse function. And now from C1 to D1, as flux is decreasing in sinusoidal nature, therefore it follows like this. And from D1 to E1, it is a constant function, so there will be an impulse function like this. And from E1 to F1, it follows the same like this. And from this you can note that with sinusoidal input we are getting non-sinusoidal output EMF, which is not desired, and this type of waveform is called as peaky waveform. Therefore, now we must discuss that what is the type of input that to be applied to get a sinusoidal induced EMF. For that, let's apply reverse engineering concept. If suppose this is the sinusoidal induced EMF, for simplicity, let's not consider the phase advance or phase delay. So as here induced EMF is taken pure sinusoidal, which will be because of pure sinusoidal flux. And now let's obtain the magnetizing current waveform by making use of this BH Castex, and which will set up the sinusoidal flux in the transformer core. And if you observe here, the current 0 point is leading and flux 0 point is lagging. So current 0 point will be here and flux 0 point is here. In practical transformer, the maximum points, that is phi max and I max, are at same instant, and similarly here phi max and I max are at same instant. Let us suppose I max be here, and similarly on negative side let I max be here. As current is leading, so current will be 0 here. Now with increase in current I, there is increase in flux, which means that with increase in flux, current I is like this, and when the core attains saturation, with increase in current I, the flux phi is constant. But if you observe here, the flux is not constant, means here more current is applied. And similarly on negative side, as flux is not constant here, which means that on reverse side more current is applied. This is the magnetizing current, which is responsible for setting up the sinusoidal flux in the transformer core, which means that for transformer we need to apply peaky waveform magnetizing current to get sinusoidal flux, to get sinusoidal induced EMF. Let's draw the magnetizing current. So what's happening within the transformer means, from Fourier analysis it is seen that a non-sinusoidal waveform can be represented with a pure sinusoidal waveform and harmonics, and the dominant harmonic is third order harmonic. So let us consider the third order harmonic. So actually in transformer, for this magnetizing current there must be flux of sinusoidal nature, and for this third order harmonic current there must be third order flux. But if you observe that with this non-sinusoidal input we are getting sinusoidal flux, means these third order harmonics are not present, which means that transformer adds harmonic like this, by which this and this will get cancelled, and the only waveform that remained is pure sinusoidal flux, and by which we are getting pure sinusoidal induced EMF. But practically this peaky waveform is very difficult. So we need to think of how to get sinusoidal induced EMF with sinusoidal magnetizing current as input. Now let's apply Fourier analysis to this waveform. So as it is non-sinusoidal, it can be represented with a sinusoidal signal and a harmonic, let that be third order harmonic signal. And why this flux waveform is non-sinusoidal means, even though the input magnetizing current is sinusoidal, the flux is non-sinusoidal. Why it is non-sinusoidal means, transformer is adding harmonics to the flux. So as why flux is of non-sinusoidal. So because of sinusoidal current I mu, this is the sinusoidal flux, and because of addition of harmonics by the transformer, this is the harmonic signal, and combinedly we are getting a non-sinusoidal signal, and because of which we are getting a non-sinusoidal output EMF. And this can also be represented with a sinusoidal signal and a harmonic signal. And now the discussion is how to get sinusoidal output from the transformer with sinusoidal input. For that we need to reduce this third harmonic signal to 0. And if you remember this concept which is discussed previously, that in alternator the induced EMF we are taking fundamental EMF and third order harmonic EMF, and the instant load is connected, because of this fundamental EMF there is current I flowing in the lines and phase of the load, but as E3 is of cophasor, that is it is a triplet harmonic which doesn't satisfy the fundamental property, so as well there is no path for the triplet harmonics from phase to phase or line to line, and these triplet harmonics are reduced by providing a neutral connection, that is by providing a path we are reducing the third order harmonics. Similarly, in case of three-phase transformers, third order harmonics are reduced by using tertiary winding which is connected in delta. Actually, three-phase transformers are to be represented like this, but to reduce the third order harmonic we are making use of tertiary winding. So is why a delta representation is also used in this representation. Now in case of transformers, as path is provided to the third order harmonic, current will flow, and because of that current there is a flux phi, and that flux phi direction will be like this, which is opposite to third order harmonic, and because of which these two get neutralized, and this is the only flux which is remaining, that is which is sinusoidal, and because of this sinusoidal flux we are getting sinusoidal output EMF, that is these two will get neutralized like this, and this is the sinusoidal EMF which is the output from the transformer. Therefore the conclusion here is that actually to get sinusoidal output EMF we need to give a peaky waveform as input to the transformer, and this peaky waveform is very difficult to obtain, so is why we need to think of how to get sinusoidal output with sinusoidal input, and for that what we are doing means we are providing a path to the third order harmonic, because of which we are getting sinusoidal flux set up in the core, and that will cause the sinusoidal output EMF. And to explain this concept we are making use of this BH Castex. So this is the importance of using BH Castex in transformers. And lastly, one point you must keep in mind that with any waveform as input, transformer will add harmonics to the flux. As here in the input signal there are harmonics, and as transformer is adding harmonics to the flux, these two harmonics will get reduced to zero, and the only flux remaining in the core is sinusoidal. And coming to this case, with sinusoidal input to the transformer, transformer is adding harmonics, and because of which flux is non-sinusoidal. And to neutralize these harmonics in transformers, we are providing path to the third order harmonics, that is by making use of tertiary winding which is delta connected, and because of which third order harmonics are reduced, and then we are getting sinusoidal output EMF. Thank you for watching. If you like this video, please like this video, share this video, and do subscribe to the channel. And see you in next lecture on switching transitions of transformers, from which you will know why transformer will drag more magnetizing current from the input supply while tap changing, that is while switching.